So next we're going to derive Bernoulli's equation, which is the statement of conservation of energy for an incompressible fluid without, I'll maybe call this friction in quotes. Technically, we'd be talking about viscous forces. So we will, maybe I'll start by reminding you of the regular law of conservation of energy, that the initial kinetic energy plus the initial potential energy plus the initial thermal energy plus the external work plus the external heat equals the final kinetic energy plus the final potential energy plus the final thermal energy. We're going to only consider the case where there is no external heat being added to the system. And so when you combine that with the idea that there is no friction, that means there's no mechanism for converting kinetic or potential energy into heat or thermal energy. That means that the final thermal energy will equal the initial thermal energy. So the conservation of energy boils down to Ki plus Ui plus W external equals Kf plus Uf under the conditions that we are considering. We are also only going to consider laminar flow. And so let's say that we have a flow field that maybe some of the streamlines sort of look like this. So we're going from a region on the left where the flow is in some more constricted area, and yet we're not too close to the boundaries, because if we were, then friction would start to become important. But if we're far away from the boundaries, then friction can be considered negligible. And then it's spreading out into a wider area here. And we know as it spreads out, the velocity is going to go down. So we're going to consider a volume of the fluid that starts here and ends here. And the red boundaries are where it is at, let's say, t equals 0. And then if we consider, so t equals 0, and then at some later time, t equals delta t, I'll do this in blue, it will have advanced. And so let's say it will have the boundary of this volume of fluid. So maybe I could shade it. Our original volume is like this. The back boundary will have moved from the red line to the blue line, and the boundary at the other end will also have moved, not by as much because the velocity will be lower over here, so maybe it has moved, let's say, about that much, like so. And so this same volume of fluid now occupies the blue shaded region, which is slightly offset from the original red shaded region. So if we think about the forces, the external forces that are acting on this volume of fluid, there is a force from the pressure on the left side, which we'll call P1, which is pushing in the same direction as the motion. And then there's also a force from the pressure on the right side, which we'll call P2, and that's pushing opposite the motion. So the work that's being done by the forces that arise from those pressures, so remember in general, the work is equal to the dot product of the force and the displacement. So for the left side, the force resulting from this pressure is in the same direction as the displacement, so the angle between them is 0, And so the work would just be the force times the displacement. On the right side, they're in opposite directions. The force is pointed to the left, but the displacement is to the right, so the angle is 180 degrees. So that introduces a minus sign. So let's introduce just a little bit of other terminology. We'll call the displacement on the left side delta x1, and the displacement on the right side delta x2. So we could say that the net external work will be equal to, as we said, on the left side, it's going to be a positive dot product, so F1 times delta x1. And then on the right side, because there's a 180 degree angle, we get a minus sign, F2 delta x2. So as before, we'll call the area on the cross-sectional area on the left is A1, and the cross-sectional area on the right is A2. And so that's going to allow us to write the forces in terms of the pressure. So the force is the pressure times the area. So F1 would be P1 times A1. So F1 turns into P1 times A1. I also want to replace delta x. So we're going to rewrite the volume. So if we think about the volume kind of in between the starting barrier, the starting border, and the ending border that I've just shaded in green, the volume of that, we're going to assume that this is a relatively small time interval. So that's some small volume, which we can write as the cross-sectional area A1 times delta x1. So I could rearrange that to solve for delta x1 equals delta V over A1. And so I'm going to that's what I'm going to substitute in for x1 is delta V over A1. And then we do the similar thing for this second part. So this would be minus minus P2A2 delta V over A2. And it's the same delta V here and here because whatever, the blue is the same volume as the red, so whatever difference there is on this side, we have to have the same difference here. So this green shaded volume on the right has to be the same as the green shaded volume on the left. And so we can see we can cancel the factors of the cross-sectional area like this, and we get that the net external work, which we could just write as external work, is equal to that small increment of volume times the difference in pressure, P1 minus P2. So that's one of the terms that we need. Then we also need to think about the kinetic energy and the potential energy. So the kinetic energy in general is 1/2 mv squared. And I want to point out that in our drawing, this region, which is shaded in both blue and red, so sort of the overlap between the blue and the red regions, that has no change in its energy between t equals 0 and t equals delta t, because it's different water molecules that are in it, but they're all flowing at the same speed and have the same vertical height as they did when we started. And so the only change in the energy of the system is going to be due to the two green parts that are shaded here. Another way of saying that is I can think of the kinetic and potential energy of this region, which is part of the red shaded region but not part of the blue, as sort of that's the initial kinetic and potential energy. Oh, here's a better way to say that. We could say that the initial kinetic energy is equal to the kinetic energy of the green region plus the kinetic energy of the overlap region, where all of this, that's the overlap region. And the final kinetic energy, and sorry, I got to be a little bit more careful. this would be the left green region. And the final kinetic energy after when t equals delta t would be the kinetic energy of the green region on the right, because that is part of the area that we shaded in blue, but not part of the area shaded in red, plus the kinetic energy of the overlap region. And so when we look at our conservation of energy equation, we can see that the kinetic energy of the overlap region is going to appear on both sides of this, and it's going to cancel out. A similar thing is going to happen when we consider the potential energy. The potential energies of the overlap region will appear on both sides, and so it cancels. So we can then focus on the kinetic energy of the green areas on the right and the left. All right, as I started to say before, the kinetic energy is 1/2 mv squared. The mass is equal to the density, rho, times the volume of that green region, delta V. And so putting those things together, we can say that the kinetic energy is equal to 1/2, the kinetic energy in general, I'm sorry, of the green regions is 1/2 rho delta V times little v squared. Okay. And similarly, the potential energy is mgy, which I could rewrite that m again as rho delta v gy. So plugging this all into our conservation of energy equation up here, we could write, and maybe I'll just explicitly include that stuff about the overlap. So the initial kinetic energy, which would be K green left plus K overlap plus the initial potential energy, which would be U green left plus U overlap plus the external work equals the final potential energy, the final kinetic energy, which is K of the green region on the right, plus K overlap, plus U green on the right, plus U overlap. So canceling out the overlap terms, and then we're going to substitute in what we have found for each of the remaining terms. So that's going to give us this. That's going to give us, instead of K green left, I'm going to write 1/2 rho delta V times V squared, but I need the velocity on the left side, which is V1 squared, plus U, oops, I canceled the wrong thing, I'm sorry. I should have canceled U overlap here, not U green left. U green left should still be there. I'm sorry. So this should be plus rho delta V G Y1, the Y position of the left side, right? So there's some variation in Y. So this is the Y position going here. So the left side is starting at a lower value of Y than the right side. So it's kind of going uphill, let's say. Okay. Then we need to add in what we found for the external work, which is up here. So plus 1/2 rho delta V, oops, I was reading from the wrong place, plus delta V times P1 minus P2. And then this equals the kinetic energy of the green part on the right side, which would be 1/2 rho delta V times V2 squared plus the potential energy of the green region on the right side, which is rho delta V GY2. So now we can do a little canceling because all the terms have this common factor of delta V. So I can cancel that out. And then we're done. So the final statement, the final statement of Bernoulli's equation is 1/2 rho V1 squared plus rho GY1 plus P1, and I'm going to take this minus P2 and bring it over to the right side of the equation, equals 1/2 rho V2 squared plus rho GY2 plus P2. So that's a 1 star. This is Bernoulli's equation. Bernoulli's equation. And remember that in order to derive this, we said viscous forces are negligible. And we also said, maybe I didn't explicitly say this, but from the drawing you can see we are comparing 2 points that are along the same streamline, right? So point 1, so we're taking the limit where these are getting quite small. So this point is along the same streamline as this point. So the 2 points have to be points 1 and 2. Points 1 and 2 on the same streamline. All right.